All right, let's do this. I'm kind of assuming most people have either watched part one or read the paper, but knowing me, if I was attending this seminar, I might not have done that. So I'll do a quick, brutal introduction so that you can hopefully have some ideas as to what's going on. Okay, so we're considering a idea in that can a network learn certain features about the world, where features are discernible objects that we humans can understand. For example, can an image classifier uh, have a neuron that will fire when it sees a cat, and vice versa? If we see the cat neuron fire, will we be able to realize that the neuron has witnessed a cat in its image classification? So this is more or less the idea behind this paper, is trying to align neurons firing with discernible features. The interesting idea they had was to consider features as vectors in a dimensional space. So let X be a feature, which will be an r-dimensional vector. Sorry, an r to the n dimensional vector. Then what they do is they try to see if they can, in a sense, have this input of a network and then sort of act on it with this W. So now this here will be W times X inside this layer, where we have M neurons here and N neurons in the input, where M is much less than N. So I think in the experiments, N is roughly 400 and M is roughly 30. And then they act on this, with another matrix, W transpose. So then what we've got here is W transpose, WX, and then they act with a value to get the final output. So the output of the network is value W transpose WX. And they had a bias in here, sorry. And then the idea is, if we call this X prime, is the loss function that they use to check if the network is, in a sense, learning these features, is they are taking the loss of the input vector X and the output vector X prime, which is the value network. So it's also worth mentioning that their experiments use sparsity as a parameter of these networks. So we're going to say each xi, which is a feature, will be drawn from a uniform distribution between 0 and 1. And each feature inside the vector will be equal to 0 with probability Si, where Si is sparsity. So, oh dear, sorry. The lights are turning off in the seminar room again. Hang on one sec.
They're evicting you.
All right. I'm actually hiding in the design department, so I feel like if someone discovers me talking about maths, they'll get upset.
Yeah,
Anyway.
It's the true design. This statement's it's a bit confusing, right? I mean, you've given two.
Sorry.
So you mean that somehow with probability Si it's 0, and if it's not 0, then you sample it from a uniform distribution, right?
Yes, sorry. That's exactly what it is.
Yeah.
So when xi is not 0, it will be taken from this random distribution between 0 and 1. And then the loss function that they use in these experiments to assess whether the network has, in a sense, learned these features is given by this. Which is a mean squared errors loss. And this is something they call the importance. And this idea comes from, say, if you have a image classifier that's trying to diagnose an illness, for example, it might consider features about that illness to be very important, whereas features such as has the person who's got freckles on their hand to be quite unimportant. And so this can vary with each feature. In most of the experiments, though, they just set it to be 1. So I think for most of the stuff I'm going to be talking about today, we can just take the importance to be 1. And then we also will sum over the different distributions of x so that we can have some experiments to look at. Okay, that's kind of like the brief intro to what Sam talked about last time, sorry. Is there any questions before I move on? All right. So the main section that I want to talk about today is the geometry of superposition section. And actually, Dan, can I get the image 0 on the board next to where I wrote geometry? I think he might have just gotten back. Dan, you there? Whenever you're ready, if you could put image 0 on the next board, please.
Okay.
So one metric that the authors used to look at the geometry of these network is something they've called dimensionality. And so I'll write that down first.
Sorry, that turns out to be extremely hard to see. You might click on it if you want to see it better.
Oh, yeah. Okay, so from the previous board, we have W here is the parameters in the network, and F is the Frobenius norm. And this is the number of nodes in the middle, or the dimension. So, sorry, I probably should say W is going to be a M by N matrix. And you can actually decompose the Frobenius norm into being a sum of the columns of W. So we'll have N columns in this M by N matrix. And so what this dimensionality is telling us is it's kind of a ratio over the features, kind of like the dimensions per feature, since we have dimensions of the embedding space here.
I made a scenario where it's kind of impossible to tell who will win and who will lose. But it's possible to tell, but it might not.
Sorry, Dan, can you beat your mic maybe?
Sorry, I must have been on a different device, yeah. I thought I was muted.
So it's worth noting as well. Have roughly that Wi will be approximately equal to 1 if the model has learned feature I, and it will be roughly equal to 0 if the model has not learned it. So in a sense, this denominator is kind of like the number of features that it has learned. And sorry, that should be an N up there, because this is the sum over the features N. So we're trying to embed N features into M dimensions, where M is much lower than N. Okay, so what they did was they plotted this more or less as a function of the sparsity on the right-hand side. So if you're going to tap on that now to have a better look, they do some rescaling. They use a log scale, and they, instead of having S, they have 1 on 1 minus S. After playing around with it a bit, it's because it makes it much more easy to look at the graph. It's quite exponential otherwise. But the thing that's fascinating is that the dimensions per feature likes to sit around this 1/2 mark for quite a while. It's more clear in the next graph. And apart from that, it sort of will change quite quickly. So they call this a bit of a phase change between these different sticky points, as they call them. I'm not sure if I find this experimenting a bit unconvincing that it's a true phase change, but it's still interesting. Especially this 1/2 dimension seems to stick around for quite a while in the dimensionality graph. But even as the authors admit, they believe that this is much more like a quirk of the model they've picked, and I think I agree with them, because I'll get to it in a second once we talk about the next picture, which
Shall I put that one
I
up?
think that, yeah, now's a great time.
Yeah.
So this picture I stared at for a very long time. This is the crazy one with, yeah, all the different colors and things. So I'm going to talk it through. I also read through the notebook that produced this graph. So I think I have some understanding of what's going on, except for these like shape diagrams that are done at the top. I'll give my interpretation of what they mean, but I can't find any definitive way the authors created these graphs. All right, so let's start with the x-axis. So you might notice that there's clumps of points. So for example, the bottom left here, I'm going to circle it. I think everyone should probably click on the image for this section, sorry, so you can see what I'm doing. So there's 30 discrete intervals where they change the sparsity. So the sparsity takes discrete values between, what values were they again? Sorry, one sec. I think it's 30 values between roughly 1 and roughly 90%. So it goes from like not sparse at all to very sparse. And then the dimensionality at the top we can see. Let's look at the pink line for a second. You can embed one feature in one dimension as just the point. And that's what happens for the first sticky point, because this leads to there being very low dot products between the features, because if you have two features, like many features in a low dimensional space, the dot products will be quite large typically, which is what we see happening over here. So to be clear, let's look at the pictures at the top now, the ones up here.
Wait, before you do
on
that,
the left-hand side.
I'm confused. So one feature in one dimension, but we have way more features than dimensions. So, but that's just what we're doing, right? It's sort of like picks for each feature.
Yep.
There's some overlaps, but that's fine. That's what's happening there. Is that right?
More or less, yeah. So I think the features was 400, and the dimensions was 30 in the paper, and then it was 20 in the notebook. So okay. I'm gonna say it's 30. So in this first section here, they just embed 30 features in 30 dimensions. So this is just like, perfect. Every feature gets its own dedicated dimension. There's no inference, and that's great. This is in the very dense region where the sparsity is, 0, s equals 0 down here. So extremely dense. Each feature gets its own dimension. Then as we move along here, we'll see the first picture they've picked here is when the sparsity is roughly about 25 to 30%. And now we actually managed to get, let's do this. There's 20 dimensions and there's roughly 29 features. There is 29 features in this one. So now we've managed to fit in 9 more features than there are dimensions.
I don't get why the number of features is varying. What? I thought it was.
So we're embedding more. We're embedding more features.
Are you saying that like the number of features we succeed in embedding, or you mean the number of features full stop?
Yes. The number of features we have is 400. When the sparsity is 0, we embed 20 features. That's the pink line at the very start. Okay. When we increase the sparsity a bit, we manage to embed 9 more features. Okay. But this results instead of all the features being their own point in space, we have these shapes. Now, what these shapes mean, so pick a colored dot. If it is not connected to another colored dot, that means that that dot product between those two vectors is 0. If it is connected to another colored dot, then that is its dot product, proportional to its dot product. So features that have these dots that are very close together, so in these like diagon ones, these have very high dot products. And then, as you can see over here, when we embed more features, they're more spread out and the dot products are lower. So we managed to embed 29 features in this first picture, and then as it goes on, it gets to roughly 60 features here, and then 80, and then I think I stopped counting this one, but it's roughly about 100 in there. And so as the sparsity increases, we manage to embed more and more features than we have dimensions. And at each, it seems, the funny thing is though, is that instead of continuously changing like the predicted dimensionality graph shows, it's clear that for each sparsity interval, the dimensionality falls into either being 0 down here, or it picks a very finite dimensionality. And the one it seems to like the best
Sorry,
is
I didn't follow that.
the digons.
0 down where?
At the bottom of the graph, sorry. So the dimensionality is 0 down here, and it's 1 up here. And as you can see, the features are either embedded at the dimensionality that is along here, or they're not embedded at all, and then they're just left at the bottom.
Okay, I'm confused. So there's so this number that you're putting along the top, like 29, 60, and so on.
Yeah, that's the number of features that it's learning.
Right. Can we not say number of features, because that should mean 400, like the number of like reconstructed features or something.
Yeah. Okay.
Okay, but then on the right hand side, this ratio is number of dimensions. But what is that? What are the numerator and denominator here? I mean, is the denominator the number of reconstructed features, or is it? Must be. Is that right?
Oh my god, I'm so sorry. I forgot to explain. The ratio here is different to the previous one. That is completely my bad.
Okay.
Yeah, that totally makes sense. Yeah, so this is still dimensionality, except now it's slightly different than the previous one.
Right, so before
here,
this ratio was the total number of dimensions, full stop, I mean the features, divided by the number sort of successfully number of embedded features, I guess. Yeah. No, so M is not the number of features, M is the number of hidden dimensions.
Yeah, M is the number of hidden dimensions. So I'm so sorry about that, everyone. That's quite embarrassing. So what's happening now is that the feature dimensionality is this new formula I've written here.
Right.
So if we embed a dimension, remember it's roughly equal to 1, and then the denominator now is how much that's made up of other features. So we pick the dimension I, we pick the feature xi, that will be that will have the direction in the n-dimensional space wi, and then we can take the dot product with its basis vectors wi with every other feature, and then we can see how much that feature is made up of other features in other directions.
Right, so how much overlap with the rest of the features.
Yeah, exactly. So maybe a picture would help here. So say if you got this feature W2 up here, then this would have been made from potentially like other features, like this one percentage, as you project it onto each axis.
Yeah.
Okay, so back to the image. So sorry, Daniel, what was your question again?
Yeah, I think I'm happy now.
Okay. So now the reason why I think, I mean this is just conjecture, but the reason I think that this 1/2 diagon pair is bless you, is quite popular is these. If you look back at the ReLU model across here, we can see that it can't actually be negative because the xi's are taken from 0 and 1, and the ReLU is also taken between 0 and 1 since there's no like constants on the outside. And so the authors think numbers, perhaps the model's not scared in a sense to put two features in the same axes in a subspace. So all those digons, for example, will look, say this is some local subspace R2 inside R to the M, which is R to the 30. Then this digon pair, we can see if we look at this graph again, that the two features that are in this pair will be completely opposite each other. So they have very strong dot products, almost overlapping, but they're antipodal. And I think this is because the model seems to think that it's quite safe to take the risk that it won't have to make x1. It won't have to make one end of the digon if it has to make the other. So as that's why we sum over the x's in the loss function. So as the model like does this many times and it thinks, okay, if I have probability the sparsity, if xi equals 0 with the probability being the sparsity, then if we look over at this graph over here, pick a digon pair. There's like 30 digon pairs in this yellow ring. If one of these antipodal pairs is 0, or if one of them is non-zero, there's a very good chance that the other one probably is 0. And so the model feels quite comfortable putting these things into digon pairs, because one of the benefits of doing this is that it gets a lot of orthogonality. So you can see that when the sparsity is between 25% down here and up to 75% over here, this whole region, it likes to use this digon pair, which is quite a long time comparatively to the other shapes it takes. And my guess is that because you get a lot of nice orthogonality in this case, most of, like every second pair is orthogonal, and when they're not, they are in the same dimension, which is not good. But the chance you got to represent both features simultaneously, I think because the ReLU output is always positive, is quite low. I could be wrong about that. That's just my interpretation.
So when they show these shapes over on the right, they're showing. So it's not. I mean,
they're showing
the pair, the kind of configurations that appear, but at any given sparsity, many of them might appear red. So it's. What does it actually mean to color it in? Like that's the predominant.
So they color it in if it's the predominant one, yeah. So It seems at this sparsity range, it likes to mostly be, these nice tetrahedrons. At this point here, we have, some digons, some triangles. And then for this big region, it's mostly just digons until, we get to over here where we start getting, this has the most shapes up here. And then as the dimensionality trends low to these like crazy weird bagel shapes, this is because it's trying to learn a lot of a lot of embedded features. And it's because now the sparsity is so high, it's pretty happy to let most features that are embedded have a non-zero dot product with other ones. And that's why you get this bagel shape.
So if we take the one that you've labeled 80 above, which is where the orange pentagon line meets the curve. So if I look at that picture, I guess I see pentagons. Those are the orbiting things. There's like a pentagon of pentagons. But then there's like this enormous mess in the middle. So am I correct in interpreting this as like the only recognizable shapes are pentagons, but there's only 5 of them, and then there's a holy mess of stuff in the middle, but that has no geometric, like nothing interesting to say about it? Or is that secretly a whole bunch of pentagons in there or something? I mean, if it's just a mess and 5 pentagons, then I don't...
I also had this question when reading this, and I scoured the notebook and the comments and everything I could find. I even watched a few YouTube videos to see how are they making these pictures, like what is their method, and I could find nothing. Maybe I did as much research as I can. If anyone's found it, please let me know. My interpretation, though, is they're doing some kind of like principal component analysis, or this technique where you can represent high dimensional matrices into, or vectors, sorry, into like 2D space. So my guess is that maybe it's just measuring the radius from 0, and it's just like plotting the angle away. And so maybe that big mess in the middle is they're not actually, that like those features that are embedded there don't actually have super high dot products. They just look like that because they've been projected. But then that doesn't explain the nice pictures in the far left, because these seem to be further away.
Are you saying you think that if I could see in 20-dimensional space, then I'd see this beautiful configuration of little pentagons?
I think.
Or something.
Yeah, that's my interpretation. I think. Sorry.
Sorry, but I thought each point in this represents a vector, right? But it isn't actually the vector.
Yep.
And then the lines are just the dot product, represent the dot products between each of the vectors. So there doesn't need to be a projection, right, for that to make that plot. This is just saying that there's some sort of, 25 kind of special features, and then a whole clump which are really strongly overlapping with each other, right?
Yeah, but it almost certainly is UMAP or T-SNE or some kind of principled projection from 20 down to 2. So it's likely that the ones that are the pentagons, they're not sort of distributed far away from each other, right? So things that are close together in this picture probably are, relatively similar vectors according to some kind of. So the fact that they all clump at the middle, it's probably not completely meaningless.
Yeah, I think they also have this picture they draw. I'll make it here for a sec. Where later in the paper they show WTW as a matrix. And this is the case where n equals 3 and n is still large, m equals 3 now. And then this matrix looks like 1, -1/2, -1/2. And this is the matrix they have, and then they express this as like columns. This is like a 2D shape like this, and they call this shape columns of W. And then they do the same thing with like a 4D matrix and draw a square. And to me, it's not super clear how they're doing this, but I assume it's the same method that they're using in this dimensionality graph. I think you're right there, Rowan, that it's like the dot products are basically what's the lines between the features are. It is strange to me though that like in the middle. Oh, sorry, go.
No, sorry, I wasn't saying anything.
Oh, I heard my own voice. Yeah, and so it seems like as the sparsity, if it was getting more and more fine, then the model would create this like huge bagel of as many features as it could embed, all with probably quite non-zero dot products.
Yeah, but that doesn't really explain that makes sense, but it's why have a pentagon of pentagons? That requires a slightly more complicated explanation.
Yeah, I think the change from the Diagon era, or the Diagon solution section in the middle, to this one here, where we have, the bagel in the middle, and then a few quite nicely orthogonal shapes that aren't connected. and then it seems to quite quickly, but change into this shape you're talking about here. And even though the importance is all constant here, so it should embed each feature with the same importance. So there's no reason why it should prefer these colored shapes more than the ones that are in the bagel.
All right. Yeah, is there anything more we want to say about this picture?
So now what the authors do, which I will talk about next, is they connect this to a famous problem in physics and maths called the Thomson problem. So I will present that, and then we will discover that this thing is actually very hard to solve, unfortunately. So let me present the problem, and then I'll connect it to the graph and what's going on here. So now we're going to let Potion use X because it's going to be confusing. Let's let UI be a point on the sphere. And we're going to let W be the potential energy. So that's going to be W is equal to the sum over these points on the sphere. So typically this is thought of as these points on the sphere are electrons, and you've got some sphere, and you're trying to find the way that you can place all these repelling electrons on the sphere such that the energy is minimal. So you want to spread them out across this sphere so that they minimize this function W. So to be clear, okay, so this has some pretty clear solutions for very few points. So if you only have 2 points, clearly just putting them on the north and south pole or any like rotational reflection symmetry like that will work. And then if you have 3 points, you can put them around in some kind of like equilateral triangle around the sphere. But this problem gets very hard very quickly. I think there's only been exact solutions found for this problem up to n equals 12, and computer-aided search algorithms that I think I only got up to 400, maybe, roughly that. That's from my research of how many have been solved. So this problem is quite hard. It's actually one of the most famous, one of the 18 famous math problems that are unsolved. I think you win a bunch of money if you solve it. So that's a bit of a shame, considering that if you looked at the dimensionality graph, it seems that these features are, in some sense, configuring themselves into these nice shapes that actually look like these Thompson problem solutions.
Is there anything beyond that comment you just made in the paper? I mean, obviously it's a natural thing to guess, I suppose, but is there any reason to think that we have two minimization problems, right? We're trying to minimize the error, the reconstruction error, and that's one loss, and here's another loss, but it's not obvious to me that they really give much evidence mathematically that those two are connected. Is that right?
Yes. They don't give much evidence mathematically, except to say that the shapes are the same. So I'm not super sure how relevant solving this is.
My impression from didn't read it as carefully as you, but I mean they see these things like square antiprisms, and I feel like that is also something that comes up in the Thompson problem, and therefore they feel like the connection is quite strong, but that it feels like about as far as it goes, unless there's some part I haven't read in the appendix that makes this connection.
No, I read through the appendix as well, and I don't think they go beyond saying the shapes look the same, which is so I think that's maybe not a bad thing for us, considering that solving this problem is somewhat very hard.
Well, solving the Thompson problem may be very hard. Connecting this reconstruction problem to the Thompson problem is almost certainly easier than that, although that's not saying very much. And that's fine. I'm not criticizing the authors, but I just wanted to make sure that I wasn't missing something here.
Yeah, no, I agree. Another thing that I thought would be worth mentioning, since it's quite relevant to this, is this lemma, which has put more precisely exactly how many, say, some kind of upper bound on how many features could you feasibly embed into n dimensions. And this is called the Johnson-Linden-Strauss lemma. Okay, so we're going to let k be a positive integer and n, and we'll let epsilon be some number between 0 and 1. Then if k is greater than this number here, then any set of points v, and n points in R to the d, there exists a map from r to the d to r to the k, where k is less than d. Such that we can bound the length of the two vectors like so. Okay, so what is this saying? This is basically saying that given a vector in a set of pick a random vector in a high dimensional space, then we can project it into this lower dimensional space with it preserving its length up to a scale factor of 1 plus or minus epsilon. And we can do this if it was like a random vector, say, we pick one at random. We could do this with probability of order 1 over n squared. So if you're in a very, very high dimensional space, say n is very large, sorry, you will fail to do this with probability O of 1 n squared. So if n is very, very large, there's a very, very good chance that you could do this. And this is...
What was the point of writing u minus v here? Oh, f doesn't have to be linear, right? Okay, so then f is of course not linear, in which case the way you said it isn't really correct, right? It is significant that it's preserving distances with some...
Yeah, it is in the proof. Though they do use a linear value for the f, like the map that there exists is linear. So what do you mean? Sorry.
Oh, okay. Well, if it's linear, then there's no point writing u minus v, right? Because f of u minus f of v is f of u minus v. So you might as well just replace this by like a single vector.
Yeah, that's a good point. Okay, yeah, sure. I could have just written that.
Okay, but you're sure that the statement is there exists a linear f?
It just says the statements I've read say just exists a map, and then in the proof I read, they chose one that appeared to be linear to me.
Okay.
I think if you had a vector...
Well, it matters very much what that kind of map is, otherwise it's kind of either tautological or... The map used for the embedding is at least Lipschitz and can even be taken to be an orthogonal projection. Oh, there exists a linear map. Well, the statement on Wikipedia says linear, so sure.
Oh, okay, sorry.
But then, okay, also the statement on Wikipedia has the way you wrote it with an FU minus FV, which is kind of weird. But alright, yeah, fine.
I think it might just be the way it's presented, because the proof I read off also used U minus V. Well, maybe that's where Wikipedia got it from. I don't know if I can give the proof if you think that would be a good use of our time, or I could move on. Yeah. All right. I'm going to probably just prove one of the inequalities, since the other one is pretty much the same, except modulo just the 1 plus or minus epsilon. Okay, so we're going to assume that k is less than d, otherwise it's probably obviously true. Then I'm going to take a random k-dimensional subspace S. And we'll let VI be the projection. VI prime be the projection onto, be the projection of the point. Into S. Okay, and then just gonna assign some variables to make the rest of this a bit more concise. We're gonna let L be this quantity and mu be this quantity. Thank you. Okay, so this proof will assume a bound that I can either prove at the end or depending on how much time we have. So the bound we're going to use, I'm just going to call it A, is if beta is less than 1, then the probability that L is less than or equal to beta on K over D will be bounded above by this.
I'm not following. So V is R to the D, is that right?
Yes.
And where do the VI's
Well,
come from?
VI is a point in V where V is a set of n points in R to the D.
Okay. I see. So, all right, a projection. So the projection. Well. Okay, so we're, yeah, okay. All right, I gotcha.
Mm-hmm. So this is bounded by this quantity, and I will prove this bound at the end. Okay. I guess we'll go to the next ones.
Yeah.
So you got a question?
No, I was agreeing.
Okay. So applying that bound that we'll take for now, we can bound this above by this quantity. So then just simplifying a little bit. And here I'm using the fact that since epsilon is between 0 and 1, this logarithm will be bounded above by this quantity here, which is the first two terms of the logarithm. we're just cancelling that and multiplying that up, we get this. Okay, but we're assuming that k is greater than a certain value in the lemma. So now doing some simplifying. So then k epsilon squared on 4 is greater than 2 log n plus k epsilon squared on 6. And then multiplying both sides by the negative, we get this. Okay, now applying this to the exponential.
I think you want to change the direction of the inequality, don't you?
I definitely do, yes. That's why I did that.
Let's see.
That's good. That's good. Oops. Okay, then we can split the exponential. This
You lost the
will be
minus
between. I did, thank you. This will be between. This will be small. This will be between 0 and 1. So this will be bounded above by just this term. Okay. What did I got? Okay. So so this is the one side of the proof, the 1 minus epsilon of the inequality, and then
can I just run through what you've done here and see if I've understood this correctly? So mu is the
yep,
L is the distance between the projected pair from this set, this sample that you took, and mu
Yep.
was the distance before you projected. And then we've shown that as n gets very large with very high probability, there's an inequality. Is that right?
exactly.
Cool.
Cool. So similarly, we can also show that. So sorry, just to maybe write it out again. So we have this, and then on the other hand, by basically the same calculation and a similar assumption, we will also have this. Okay, now we're going to let this f be.
Wait, now I'm confused. Why shouldn't it be 1 plus epsilon in the upper bound and 1 minus epsilon in the lower bound?
So what we're going to show here is we're going to we're trying to establishing the section where this won't work, if that makes sense. So we're
Oh,
going to
of
show that
course.
this
Yeah,
region
yeah,
is very
so,
small.
yeah, yeah. Okay.
Yeah.
Yeah, makes sense. Mm-hmm.
Yep. Okay, so now we're going to set that linear map that I teased earlier. So this is a scalar in the front. All right.
I see. So it's when I first saw this lemma, I thought, "Ooh, there's some clever linear map that does it," but that's really not the point of it. It's like
No.
basically you find any linear map, like you pick any projection, and it works. I guess there's this scale factor, but who cares? Yeah.
So now I'll just substitute once again in my mu and my L. I just define those to make this get shorter to write every time. Okay, and then I can substitute in my F. Oh, sorry, I kind of did something here. So I moved the d of a k to the other side, and then I brought it inside the square root. And then I'm going to call this thing my f. So I'm going to replace it with f. I didn't actually just sub it off there.
An inefficient way of doing.
So yeah, I think it's quite important for this to work, for it to be linear, as you can see here. Okay, so then again, this is bounded like so. And remember that this thing that we proved earlier is bounded by 1 on n squared. Is there a copy and paste feature on this? No, I don't think so. Okay, so what this is saying is that the probability that this quantity inside the probability sign here is not in the range of, I'll sort that out. Okay, so in the worst case scenario, the probability that this quantity star, which is the division of the two norms, is not inside the range that we want, is at most 2 on n squared. Okay, so if we were to then say So then if we pick 2 points, the probability they lie outside the desired range is going to be at most n choose 2 points, where the probability that they're outside the desired range is now 2 on n squared. And then n choose 2 can be expressed as n minus 1 n on 2. So this is this 1 minus 1 on n. This can be thought of as like the lower bound on the desired probability of what we want. So this is like the worst case scenario, is that the probability that you pick 2 points and they lie in the range you want is going to be this number here. So if n is very large, you say if n is like 1,000, then there's a very good chance that the 2 points you picked will be inside the desired range, because it will be like very close to 1. So therefore we have 1 minus epsilon is in that range with probability at least that. And that's pretty much the proof, modulo proving that bound that I assumed.
Yeah, I think we can skip that.
Yeah, agreed. How am I doing for time?
Yeah, thanks. That was worth seeing. So we're going back to the tool models.
Yeah, I wanted to talk a little bit about the non-uniform superposition case. Oh, I think also maybe I'll just draw a quick picture that I find helpful. So like say you've got a one-dimensional line of like a 1D vector, and you say what's the probability that I could pick another vector in that space that is orthogonal to this vector? Well, here it's 0. The question doesn't really make sense. But if instead in a 2D sphere, a 2D circle, if I had a vector, say, going from 0 to the top, then the probability you pick to a vector that is, say this is distance epsilon, that is orthogonal to that, is going to be inside this range here. And then similarly on the sphere, it's going to, if the vector that you want to be orthogonal to is this one, well then you've got this whole equator of choices to pick one that is almost orthogonal. So you can see, and then I'll leave the 4D case as an exercise for you guys later to visualize. But you can see here that each time the dimension grows, you get many more choices to choose vectors that are orthogonal. So that's why this lemma is of importance, because the model in the toy models paper wants vectors to be orthogonal, because these vectors are features, and we don't. If we want to look at a model and be sure that this feature is there and not just some crazy combination of other features, well, if they're orthogonal, then it's quite clear that the feature is the one that is present. Okay, let's maybe get the next picture up, Dan. This is the, sorry, I'm not using the number system we agreed on. Number 2, 3?
3, I think. Yeah.
It's like got the pentagon and the diagon.
Again, I think the link between this lemma and what they're saying is not meant to be taken too literally, right? So for one thing, I mean, our projection is definitely not a linear map, and somehow presumably we're doing better than the lemma would let us do. Is that right? I mean, like somehow
we're doing better.
Well, the motivation for the lemma is to say that if you allow some error, then you can pack more vectors than you think, but it's not like the precise, like you know, whatever figure it was. If I open up the lemma again, the lemma says.
Oh, so you're saying the model's allowing for a much larger error and just packing way more stuff into it.
Well, I mean, there's this particular lower bound where k has to be greater than or equal to 4 on some polynomial in epsilon, right?
Yep.
And so it's not like these particular values in the lemma really have any bearing to what we're seeing the model do, right? It's just a general point that if you allow some kind of non-zero dot product, you can fit more than you think, or something like that.
Yeah, exactly. Especially in super high dimensional spaces, like the ones that this model is trained on. Okay, so once again, we're going to look at this graph a fair bit. So now we have 5 features with 2 dimensions, and once again, the importance of all of these is going to be 1, except when we choose to vary the importance of one of them. So this section here, this picture, talks about non-uniform superposition, which is the case where not all features have equal importance. So the thing that's interesting here is that, once again, as a function of sparsity, as you vary the sparsity
sorry to interrupt again, Ben, but now I'm confused. So I thought all the experiments we were talking about had this kind of decay schedule for the importance, where there was one direction that had importance 1, and then the next one was like 0.9, and the next one was 0.9 squared.
No. The last graph, sorry, was all uniform importance. And the weird shapes one. That all had importance 1.
I see. Okay, thanks.
Yeah, this is when they jump around a little bit. And this is when, once again, they remove the importance of all of them. So actually, in this case as well, sorry, this is uniform importance. Because this is non-uniform superposition. That's the difference, not the importance. Yeah, the importance is still 1.
I see, but somehow not all the features are equal, because instead of, like before, they were varying the sparsity of all of them simultaneously.
Now it's 1, yeah.
Yeah, but now they're just doing 1, right?
And I think the idea of why they do this is they can show that they want to show that uniform superposition is, in some sense, a perturbation theory of the uniform case.
Okay.
So we can see here on this pentagon-diagon phase change at the bottom, we can see that the top left graph stays as a diagon regime for certain values of sparsity of this 5th one that they vary in the middle. And then as soon as it crosses over this certain range of this certain value of sparsity, then it switches to this pentagon regime. And then as it gets more and more sparse, these arrows show how the pentagon changes as it goes up the loss curve. They don't really go much beyond this one graph for the non-uniform case. They just sort of use it as a yardstick to say, hey, look, it seems as though we can think of non-uniform sparsity as perturbing the sparsity of 1. So they fix the sparsity of all others and then just change the sparsity of one feature and see how that affects the graphs. And then they do a similar experiment next where they will vary the sparsity of pairs of features, or what they call correlated features. So I don't think I sent a picture for that one, but in a similar vein.
I do have one more picture. Is that the one? Oh, there's a couple more.
Oh no, sorry, those aren't the ones yet.
Okay.
Those are, yeah, the correlated feature section is, instead of varying the sparsity of, say, 1 point, they vary the sparsity of pairs of points. And these pairs of points will now be will now be non-zero with the same probability. So maybe I'll write this down. So when you have this case with the features come in pairs, or maybe not pairs, but high dimensional spaces, then the model prefers to, so here I'm going to say, so we have 4.
I don't
We'll do
understand
an
what
n
you've
equals
just
4
written
case.
here. So they're non-zero with probability p equals si. And they're either both zero or neither are. What does this mean? So you just
so they're either both zero with probability si,
right, okay.
or they're neither zero. So they can be thought of as like being linked in the.
Okay, so when you're sampling, I mean, the definition of the distribution of vectors is, for all the other coordinates, you do what we said before, but for these two, you sample according to the probability s, and then if it so with probability s, you're supposed to actually sample both of them independently from a uniform distribution, x1 and x2. And
Yep.
Otherwise, they're just both zero. Is that right?
That's exactly right.
Yeah, okay.
Thank you. So in that case, so we have 4 features, and the embedding dimension is going to be 2, just so we can draw a picture. And I'm going to indicate correlated features, perhaps just with color. So here x1 and x2 are correlated, and x3 and x4 are correlated. So then when the model tries to embed these dimensions, it prefers to have correlated features be orthogonal, which would make sense since you want features that occur at the same time to be orthogonal, because you want to be able to discern which feature is which. So this is one of the results of the model, is that it embedded these features like so, where so x1 and x2 are orthogonal, and x3 and x4 are orthogonal. So the model can, because since the model was trained to tell that these features always occurred together, or they didn't, it seemed to like to put them in orthogonal spaces. Similarly, there's anti-correlated features, which, as you might guess, is if one is non-zero, then the other is zero. So say if these are anti-correlated, if x3 is drawn from the uniform distribution and not zero, then x4 must be zero, and vice versa. And similarly for these ones, if x1 is drawn from the uniform distribution between 0 and 1, then x2 is 0. In that case, it's quite similar, but it would like to put them in the same plane, since it knows that these features never seem to occur together. Which, once again, makes sense. You know, it wants to keep the ones that are in nice pairs. What time is it? Ooh. Okay, actually, let's just maybe post the next 2 photos, and I'll just verbally talk over them in the last 5 minutes.
So what do you want to say about these correlated features? I mean, these are definitions, but what's the point of introducing these?
Oh, mainly that the model can also learn to do the same thing if you vary the sparsity of one feature and if you vary the sparsity of multiple features, that it doesn't break anything. It still does it, which is maybe unsurprising.
Okay. Yeah, let's move to the next set of boards and I'll post the pictures there. If that's all right.
Yep.
Just one next
So
to
I'm
each
not
other?
sure. Yeah. So these are ones that will indicate what's happening over the training of a model. To my knowledge, these aren't probably super relevant for SLT, just because I think we don't really talk much about like gradient descent or how the models are trained in the Bayesian context.
You'll have to move
But if you'll
left a
tap on
bit
the
for the orb cam.
Oh yeah, thanks. But if you'll look at the left-hand side for a second, every individual color here is a specific feature, and on the bottom of the x-axis for both are the ticks of the training, so how long it's been training for. And the top one shows the feature dimensionality, like in the first graph, with all the funny pictures and all the different digons and trigons and tetrahedrons. And the bottom one shows the loss. So looking at the top left for a second, we see that each feature will sort of approach a finite dimensionality over training. So this is just the model learning to put them into the dimensionalities it wants to have them in. So as you can see in this case, they all either go to 0, not being learned, or into a half. So this is going to be an example of the diagon solution, where we have pairs of points in local R2 subspaces. The thing that's interesting to me though is that the loss seems to change quite drastically once it like moves around these features. So it seems to realize that if I put this feature into this dimensionality, then all of a sudden, I get a big drop in the loss. I get rewarded quite well. Which I thought was interesting, considering that the importance is supposed to be uniform in this context. And so I don't see how putting that feature up there resulted in such a good uniform loss. It could just be a certain amount of features at this stage. And the graph next to it is also quite similar. It's also showing features that are sort of, this is showing the shapes case. So the left-hand side just shows the dimensionality, and the right-hand side is now we've got some correlated features. So here the blue ones are correlated and the green ones are. So the blue ones will occur together and the green ones will occur together. And you can see initially that if you look at the B section, they seem to be moving away from each other together into like as far away as possible. And then once they hit sort of the roof of their capability, they start to spread out in this 2D plane until they arrange themselves into this octahedron shape.
So these two
and
rows,
each time
these just represent different hidden dimensions, right?
Sorry, what was that?
So the top row has m, what is it, n, equals 2, and the bottom is 3. Is that the only difference here?
Between the two graphs, sorry, or the
two rows of the right-hand board here. So...
Oh, yeah. I think the top one's just like a top-down view. It's the same picture.
Oh, I see. Okay.
Yeah. Although maybe it actually would be the same if you embed it into m equals 2. It's interesting. But yeah, it seems that as it approaches more and more like stable solutions, you see like this like very drastic drops in the loss. Like for example here, and then a bit at the end when they spread out, and they get a lot when they move down. Dan, you might know better than I, but I don't know if SLT would have anything interesting to say about training data or what happens over training. I mean, I guess it's just like what happens is what happens. It learns the stuff better and it finds a better arrangement for the features.
Well, either this slide just is nonsense, or it occurs in a high percentage of training runs, in which case it's nothing to do with any particular trajectory. It's more to do with the structure of the loss surface, right? So
yeah,
if it's to do with the structure of the loss surface, then, well, presumably these circles you're drawing represent regions of very high slope, potentially. But yeah, what that has to, I mean, it's tempting to look at this picture and, think about it as being something like a phase transition, but
yeah.
And it's maybe not crazy to think that, but
the authors seem to call it that, or they seem confident that is what's happening here.
Yeah, I think it's appropriate language potentially, but I do worry a bit that people are jumping to use the thermodynamic language in like a sort of colloquial fashion, which might dilute its utility if it's sort of comes. I mean, if phase transition comes to mean any time a loss plot decreases quickly, then, well, that's actually not very helpful. But I mean, more convincing is, I suppose, that the difference between the second and the third column, and the first and the second column, okay, those would represent different kinds of solutions, so they would probably be, the transition between them does seem like it's likely to be a phase transition. And then if there is a phase transition, you might see it in the training steps versus loss graph, and you might see it in other kinds of graphs as well, but I don't think just looking at this graph on its own, I mean, if I just saw this graph, I would be quite skeptical a priori that it's evidence of a phase transition, but combined with the first two rows, the thing above it, I think it's probably legitimate, although one, I think, has to argue a bit harder to really make this case. Yeah.
No, I would agree. Okay, since there's only a few minutes left, I think I might just stop there.
Yeah, thanks a lot, Ben.
Any questions, please? No worries. Once again, this is much more like what I got out of reading this paper. Maybe others could obtain further knowledge that I couldn't extract.
Yeah, I think at this point we've probably covered it. There's other stuff in there, of course, but I feel like this is the stuff that
I don't want to dismiss the rest of it, but I read the rest of it and it seemed like it was still good, but it was just more like, I guess, what you asked when I introduced the correlated features and the other sparsity deformation. Like, it's just more of like examples of like similar ideas in different contexts. Yeah. All of which are interesting, but yeah, I'm not sure if it's anything new. The nugget of it seems to be the phase transitions that Sam talked about last time, and perhaps the dimensionality graph.
Yeah. Yeah, to reiterate, I think it's a very interesting toy model, and probably something we can profitably study with a lot more attention to, say, understanding what these phase transitions are and what the geometry is and all of that. Hopefully we can have a crack at over the coming months.